Today we will be seeing various distributed energy resources, specifically combined and heat power plants. Renewable or non-conventional electricity generators employed in microgrids or DG systems are known as distributed energy resources or microsources. And choice of distributed energy resources depends on the topology and climate of the region and its availability. Since microgrid integrate varieties of distributed energy resources that are intermittent in nature, wide range of control is also necessary in microgrid to guarantee optimal operation, system security, emission reduction, and seamless transfer from one operating mode to other without going against system constraints. So here distributed energy resources are listed here. CHP, combined heat and power systems or cogeneration systems, wind energy conversion systems, solar photovoltaic systems, small scale hydroelectric generation, storage devices, electric vehicles, micro turbines, and other renewable energy resources. So let's start with CHP system, combined heat and power system. They are the most distributed energy resources for microgrid applications. The key feature of the CHP system is sensible utilization of waste heat, thereby achieving energy efficient power generation. And here the CHP is also called cogeneration. It refers to the use of recovered exhaust heat of any production unit for another process requirement, and the byproduct heat is captured and used by CHP systems and can be used locally for industrial and domestic heating purposes. So hence CHP systems are located very close to the loads. Here we can see in the pie chart 45% of the heat which comes out, it can be used for any other purpose, whereas 15% here in this 15% can't be used, it goes out as heat loss. So if we use this 45% and this 40%, total output become this 45 plus 40, total 85% energy output, right? So by using cogeneration system, the energy output can be enhanced to 45 to 90%. Okay. So without cogeneration, the conventional power plant, the efficiency is only about say 35 to 45% only. But with cogeneration, that is by make use of this waste heat, and by utilizing this waste heat, the efficiency can be rises to 80 to 85%. If the heat is transported to long distances, usually heavily insulated pipes, the overall efficiency will decrease, right? So when it is utilized locally, it is more effective and become more efficient. And commonly the CHP plants are employed in heating systems of hospitals, big towns, or oil refineries, paper mills, and especially with large heat loads. CHP does not have to be a renewable source of energy. In many cases, they make use of natural gas, and the use of biomass as a source is the only renewable form of CHP. So let's come to micro CHP system. Typically, micro CHP systems are installed in smaller premises like small commercial buildings or homes. Most of the large CHP units generate heat as the byproduct and electricity as the primary product, whereas micro CHP systems generate electricity as the byproduct and heat as the primary product. Heat demand of the consumer is the main parameter which decides energy generation by micro CHP systems. Here, micro CHP systems frequently generate more electricity than demanded, and they're fundamentally micro turbines coupled to high speed, usually 50,000 to 1 lakh rpm, single shaft permanent manual synchronous machines with magnetic bearings or airfoil. And here they are provided with power electronic interfaces for connection to the electrical loads. So for extracting low and medium temperature heat, they are incorporated with their own heat recovery system. And this micro CHP system, they are cheap, reliable, and robust, and they are available in the range of 10 or 100 kilowatt capacity. Now we can see how it works. So during operation of a CHP set, the pressure of the incoming air is raised. That is, by passing through the compressor, centrifugal compressor, pressure of incoming air is raised during the operation. Temperature is then increased by passing this compressed air through a heat exchanger. Then in combustion chamber, the hot compressed air is mixed with fuel and burnt. Mechanical power is then produced by the expansion of high temperature combustion gases in turbine, which in turn produce high frequency electrical power by driving this permanent magnet. So using a rectifier unit, this high frequency output voltage is then converted into DC, and using an inverter unit, the DC voltage is then reconverted into a 50 Hz or 60 Hz AC. Now we will see the advantages of microgrid using micro CHP plants, and here full utilization of waste heat is achieved in microgrid by proper positioning of micro CHP plants near heat loads. And here the level of heat generation for micro CHP plants is generally small. So here we can say it is flexible in matching several small heat loads. And here combined generation of electricity and heat can be optimized by designing a microgrid by mixing non-waste and waste heat producing generators. Still, there are chances of mismatch in generating a proper mix of electricity and heat. Therefore, we need to pay attention to improve the flexibility. Primarily, these micro CHP systems are based on the following technologies: IC engines, that's internal combustion engine, Stirling engines, micro turbines, and fuel cells. So let's come to IC engine first. So here combustion happens inside the combustion chamber with or without oxidizers. And commonly used fuels are diesel, petrol, gasoline, natural gas or liquefied petroleum gas. And here liquid and gaseous biofuels like ethanol, biodiesel also can be used. Here combustion creates high temperature and high pressure gases that are allowed to expand and act on movable bodies like pistons or rotors. So here we need to provide a spark in the ignition for a petrol type of IC engine, or we have to provide compression ignition in other types of fuels. The next one is Stirling engines. Here combustion takes place outside the chamber. The external combustion engine uses the combustion process to heat a separate working fluid, which then works by acting on a movable parts. Here heating can be done by solar or any other resources. And here basically the Stirling engines uses an external heat source and an external heat sink, and here the working fluid is normally the combination of air and hydrogen or helium gasoline in a sealed chamber. Different processes are the cooling, compression, heating and expansion. And a hot heat exchange is kept in thermal contact with an external heat source, while the cold heat exchange is kept in thermal contact with an external heat sink like radiator. Here when the gas is heated, it expands in the sealed chamber and acts on the power piston to produce a power stroke, and when the gas is cool, its pressure drops and then less work has to be done by the piston to compress the gas on the return stroke. And here the primary heat source enters the heat engine heater and produces a mechanical power, and the waste heat from the engine's heater can be used for heating applications. Advantages of Stirling engines are they have high energy conversion efficiency, and they're more reliable and require low maintenance, and they are free from pollution. The drawbacks are the size is large and it requires high capital cost. Typically they are used for water pumping and electrical generation. This is a typical Stirling engine using a solar concentrator. Here we can see a dish type antenna, and a lot of mirrors are sticked on the dish antenna to concentrate the solar energy to a single point, and at that point Stirling engine is kept and output can be used to generate electrical energy. Now we will see the third technology, micro turbine. You can see here the block diagram of micro turbines. The inlet air is compressed and this air goes to the recuperator and it enters to the combustion chamber, and fuel also reaches here the combustion takes place Then hot gas or steam enters the turbine and the turbine is rotated, which is coupled to the generator, and the generator produces the electricity. Turbine out hot air, which goes to the recuperator, and this heat energy is partially used for heating the inlet air and remaining goes as waste heat. The output of microturbines range from 25 to 300 kilowatt, and their thermal efficiency is increased using recuperator, so the waste heat is used for heating the incoming gas. And microturbines are available in two forms: single shaft or split shaft. So let's see the parts of a microturbine. Main parts are turbine. Normally they are high-speed gas turbines. Turbine is coupled with an alternator, and there is some set of power electronic devices. Usually in single shaft machines, frequency is high, typically 1500 to 4000 hertz range. And so this AC voltage generated by the alternator has to be converted into a standard power frequency. So we need some power converters. And then comes recuperator. Recuperator improves the energy efficiency by recovers the waste heat. Last one is control and communication. Turbine control mechanism, inverter interface, startup electronics, instrumentation and signal conditioning, data logging, diagnostic and user control communication, etc. They all are included in control and communication systems. So in single shaft microturbines, the turbine is directly coupled to the generator, and the output of the generator is rectified and then inverted to get the output. Here the speed is in the range of 50,000 to 1,20,000 rpm. So alternator also has to rotate at this speed because they are mounted on the same shaft. So here most microturbine use permanent magnet synchronous generator or a synchronous generator for power generation. This high-speed PMSG has drawbacks like it undergo thermal stress, demagnetization phenomena, centrifugal forces, rotor losses, etc. The main drawback is that though they are cheaper and robust, their speed is load dependent and they cannot be connected to the grid without the use of expensive power converter systems. Then the use of electronic inverters or interfaces, they introduce harmonics in the system and reduces the output power quality. We can avoid the drawbacks of that single shaft microturbine here. Here we are using gearbox to reduce the speed so that output is directly 50 or 60 hertz. So advantage of coupling the synchronous generator, eliminate the use of power converter. And in turbines, 50 to 60 hertz power will be generated by synchronous generator coupled with microturbine via gearbox. Thus, the need for power converter and rectifiers units are completely eliminated. The main features of microturbine are it can supply customers' baseload requirements, or it can be used for standby, peak shaving and cogeneration application. Peak shaving means the process to smooth out the peak loads, which we will see in detail later, and it can also be used for cogeneration application. And the second point, as compared to other distributed energy resources, they are comparatively smaller in size, and here the efficiency is more than 80% if we utilize the waste heat. And coming to the emissions are lower than 7 ppm for natural gas machines, and it has good life of 45,000 hours, and it is economical, and fuel flexibility is the acceptable noise level and vibrations the, and installation is also simple. Next technology is fuel cell. There are different types of fuel cells. Basically the fuel cell convert chemical energy into electrical energy, and just like battery, it consists of two electrode, anode and cathode, and an electrolyte. The reactants and products are not stored like battery, but they are continuously fed to the cell. And here during fuel is supplied to the anode side, and here the air is supplied to the cathode side. So electrochemical oxidation and reduction take place at the electrodes, just like battery, to produce electricity. So here heat and water come out, their two byproducts are the single fuel cell produce output voltage less than 1 volt. So we need to connect many fuel cells in series to get higher voltage. So let's see different types of fuel cells. The first one is proton exchange membrane fuel cell, abbreviated PMFC. This type of fuel cells are portable. It can be used for transport applications. One is phosphoric acid fuel cell, abbreviated PAFC. Their operation is at 200 degrees Celsius and they can be used for stationary applications. The third one of fuel cell is molten carbonate fuel cell, abbreviated MCFC, and they operate at 650 degrees Celsius or above, and they are currently used for biogas, natural gas, and coal-based power plants, political utility, and military applications. One is SOFC, or solid oxide fuel cell. They have solid oxide or ceramic electrolyte and they operate at around 1000 degrees Celsius.